Let's take a look at our problem for today. I want to find the maximum and minimum values of the function x squared minus 16y squared plus 18z squared, subject to the constraint x squared plus y squared plus z squared equals 1, if such values exist. Always a great result in math class, trying to solve a problem, and there might not be an answer. Fun times in math class. Notice that this problem has seen an upgrade from the previous problems that we've been doing with these Lagrange multipliers. Instead of trying to optimize a function of 2 variables, we're optimizing a function of 3 variables, and our constraint is also in 3 variables. I do like to keep things similar, so let's take a look at the constraint. The constraint is x squared plus y squared plus z squared is equal to 1. And so this is a sphere. So put that in the chat. So the first problem that we did when we were working with Lagrange multipliers was to optimize a function subject to a circular constraints. And we were looking for the level curves of the function that were tangent to the constraints. The constraint was a level curve. We could imagine the constraint as being a level curve of the function and of the constraint function. And we're trying to optimize the objective function by looking at its level curves and find out which ones of those are tangent to the constraints. We've just gone up 1 dimension. So now our constraint is a 2-dimensional surface in R3. And we're going to look for the same thing. I want to find level surfaces of, so this is a 3-dimensional solid in 4-dimensional space, our objective function. So our objective function is a 3-dimensional solid in R4, but we're looking for the same thing. We're looking for a level surface of F that's tangent to the constraints. So we're still looking for the same thing, a level surface that's tangent to the constraints. Just like before, we're looking for a level surface of F that's tangent to the constraint in the same way that when we had a function of 2 variables, we were looking for a level curve of F that was tangent to the constraints. And that means we want the same thing. We want the gradients to go in the same direction. So we still want the gradients pointed in the same direction. So although geometrically this problem seems a lot different, we're still after the same thing. We're still going to apply the same method. I did also want to take this opportunity to take a look at, this won't show on the video. Oh, actually, no, I can do that. I wanted to take a look at level surfaces of the function f. So let me share screen. So let's take a look at these surfaces. So I've just looked at various level surfaces of the function f. So I have x squared minus 16y squared plus 18z squared is equal to 2. And then I just plugged in some different values to get different level surfaces. I don't have a 4D plotter, I think if I did have a 4D plotter, I don't think I would be able to comprehend what I was looking at. So I'm going to have to look at it in pieces. I'm just going to have to imagine this four-dimensional object by looking at its level surfaces. So as we decrease the constant, so here's f of x equal f of x, y, z equals 2. If we drop to f equals 1, I get a similar hyperboloid in one sheet. So the one sheet just means it's just one big piece. We just get this giant Lexus grill in 3D. When we drop the constant down to 0, we get this infinite elliptic cone. So what's happened is that hole through the center of our hyperboloid has been pinched down to a point. I don't know why they have to film these at Batman angles, these crazy Dutch angles. Just, I don't know why they can't just make the X flat. But anyway, I'm just getting distracted. You can see that what's happening is that that hole that in the one sheeted hyperboloid no, we're gonna have to look at it by the scale. The hole is getting smaller. So notice that this hole, the holes look the same, but if we check the scale on the X, here we are from -10 to 10, and we got this big hole. And then as we decrease the constant value of F, that hole is getting pinched together until it drops down to 0, in which case we stop getting the hyperboloids and we just get these elliptic cones. Then when the value of F goes negative, it's pinched so hard, we end up it pinches the two parts apart, and we end up with a two-sheeted hyperboloid. And then the more negative it gets, we'll just change the shape of each of the sheets. Notice that the scale on the X here goes from -4 to 4, and the scale on the X here goes from -5 to 5, and these take a long time to graph. So we can't look at a four-dimensional picture of the solid F. So we're going to have to look at it with level surfaces, all the different values. Just pick different values. The good news is, in the first problem, the first time we did this constrained optimization problem, we worked the problem geometrically. I made life simple on us. I just gave us a plane, and we looked at where the level curves of the plane were tangent to the constraints. We're going to do the same thing here in this problem. We just can't picture it quite as well, because I don't want to have to draw all these different surfaces. But we're looking for these one-sheeted, two-sheeted, or elliptical cone to be tangent to the sphere, x squared plus y squared plus z squared equals 1. That sounds like a lot, but it's something that we've already done. It's a great thing about math classes when you can look back to something that you've already done. We're just going to solve the system where the gradient of F is equal to some constant times the gradient of G. That's having the gradients pointed in the same direction. The only difference is the magnitude, but the direction is the same. And we're still subject to G is equal to a constant. So we still want this same system of equations. So let's begin. We need derivatives with respect to x. So I need an fx. Fx is 2x And lambda gx will be 2 lambda x. We need to do this fy. So fy, the derivative of f with respect to y, is going to be negative 32y. And lambda gy is going to be 2 lambda y. Fz is going to be 36z, and lambda times gz is going to be 2 lambda z. Our three equations are going to come from our first derivatives, and our fourth equation will come from the constraint. So we're still looking at a system of equations, of a system of 4 equations and 4 unknowns. Just that 3 equations were summarized in that first vector equation. So here's our system. I'm going to divide by 2, and we see from the first equation, we get x is equal to lambda times x. Our second equation, I'm just going to divide by 2 again, and we're going to get negative oh yeah, okay. I didn't do the right function. So we'll have negative negative 32, divide by 2, negative 16y is equal to lambda times y. It's been a question, the y isn't squared in fx. Did I prep the entirely wrong problem? Wow, I did. All right, I'm just gonna have to start over.